Today in this video, we're going to learn about the basics of complex number, the forms they take, and also finding the roots of complex number. First, as you can see here, complex number can be written as a plus bi, where a is the real part of the complex number and bi is the imaginary part. A and b are real number and I is the imaginary number, which is equal to the square root of -1. So this form is the Cartesian form as annotated below, and we will come back to this in the latter part. And how are we going to present a complex number? First, you're going to need an Argand diagram. So basically, you just need to draw the traditional x and y axis, but instead of the x and y, we're going to replace it with r and I. So r is in the horizontal axis, which represent the real part, and the I is the vertical axis, which represent the imaginary part. So let's take an example of 4 plus 3i. Here we see that 4 is the real part, thus linking it down to the horizontal axis, and 3i is the imaginary part, so we linked it to number 3 on the vertical axis. And then when we got that point, we're going to link it back to the origin, so 0. And thus that is how we are going to graphically present complex number. And actually in this example, we have 4 plus 3i and 4 minus 3i. These two are actually each other's conjugates. So the only difference between these are the sign in front of the imaginary part. So we can say in the more general form that a plus bi is the conjugate of a minus bi. This is going to become handy when you start learning about complex roots of polynomial function and such. Now we're going to move on to polar form of complex number. So before, we have already looked at the Cartesian form, which is a plus bi. Now here we have polar form, which is written as the absolute value of z times cosine of theta plus I sine of theta in bracket. So the absolute value of z in question is the modulus, is called the modulus, and theta is called the argument. So what is the modulus and the argument? Let's draw an Argand diagram to visualize this. So we're going to use our previous example of 4 plus 3i. Here, the orange line is the modulus, so basically the distance from the origin to the complex number itself. You can imagine this as a triangle. So zooming in, you can see on the left, we can see that the modulus is basically the hypotenuse of the so-called triangle, and thus we can use the Pythagoras theorem to calculate the modulus, and in this case it will be equal to the square root of 4 squared plus 3 squared. And again, for the argument, we're going to use the trigonometry property and to find the angle in question. So there are many ways. You can use tan minus 1 of the opposite side over the adjacent side, or you can use sine minus 1 or cos minus 1. There are two things to know. So the modulus has to be a positive value. As we have seen earlier, it's written as the absolute value of z. And second thing is that there's a range for the argument. It has to be between minus 180 degrees and 180 degrees. If you're going to write this in radian, it can be between negative pi and pi. This is really helpful to remember in questions because some is going to involve negative value of imaginary part or real parts of the complex number. Now let's try to condense everything in one example. Here they ask us to find the polar form of 2 plus I. So we know to find the polar form of a complex number, we have to find the argument as well as the radius. First, it's advised to draw an Argand diagram. So here I'm drawing the diagram and our complex number. And after that, you can always start with the modulus. So as mentioned, the modulus is technically the distance from the origin to the complex number. So you can use the Pythagoras theorem, as we can imagine this as a triangle. So we will have the square root of 2 squared plus 1 squared, which is equal to the square root of 5. And next, for the argument, again, imagining this as a triangle, we can use trigonometry. And in the question itself, we already have the value for our adjacent side and opposite side of our so-called triangle. And so we'll have the argument equal to tan minus 1 of 1 over 2, which is equal to, if you plug it into the calculator, you will have 0.464 radian. And if you want to present it as degree, you can change the mode on your calculator, and thus you'll get 26.6 degrees. Now we already have two components for our polar form, and so writing our final answer, it'll be the square root of 5 times cosine of the argument, which is 26.6 degrees, plus I sine of 26.6 degrees in bracket. And similarly, if you want to write it in radian, you just need to change the argument value, which is square root of 5 times cosine of 0.464 radian plus I sine 0.464 radian. And most of the time, students will prefer to use radian, so you can also keep that in mind. Here, there's a trick that will make everything easier and much faster to write. So instead of cos theta plus I sine theta, you can use an abbreviation. So basically, cos theta plus I sine theta can be written as cis theta. So you can combine them into one word like this, which will save you so much time. So here's an example. You can try converting complex number into polar form. So we have minus 1 plus 3i. This is the Cartesian form. You can, of course, pause this video and do it yourself at home. And so, first, I'm gonna draw the Argand diagram. Okay, so first, the easiest is finding the modulus. So the modulus is equal to 1 squared plus 3 squared, which is equal to square root of 10. So coming up next is the argument theta. And some students might mistake at this part, because if you do it the way that we did previously, which is to take tan minus 1 of let's say 3 over 1, this is wrong, because if we're doing this, we are finding the angle of this. However, the argument is the angle that the complex number make with the real part, the real axis, the positive real axis. So actually, the argument has to start from this side. So it is actually this angle. That is the argument. So of course, you can still try to calculate this part, and eventually you can take 180 degrees minus this, or pi minus this, let's call it alpha, to get theta. So let's remove this and put in alpha is equal to tan minus 1 3 over 1 plug it in the calculator, we get 1.25 radian. So theta will be equal to pi minus 1.25 radian, which is equal to 1.89 radian. So from here we can write it in the polar form. Square root of 10 times cis 1.89 radian. So from here, we just need to note that the argument is the angle that the complex number make with the positive part of the positive axis of the real part. So it's this one. And if it lies in the third quadrant or the fourth quadrant, it's actually this, and this is the argument. And this is because, and the reason why it's not all the way over here is because of the range that we discussed earlier, that the argument has to be within minus pi and pi, or minus 180 degrees and 180. So yeah, that's it. And comment below if you get this right or not. One thing to note about polar form is the sign between cos theta and I sine theta. Here you can see there's a negative sign between them, making it not a polar form, since a proper polar form has to strictly have the positive side. And there's a simple solution to this on how to convert this into a proper polar form. Here you can see cos theta minus I sine theta is equal to cos negative theta plus I sine negative theta. Here we have a proper polar form. And the reason for this is because of the trigonometry property. You can see that cos theta is equal to cos of negative theta, and minus sine theta is equal to sine of minus theta. You can check the sine and cosine graph to verify this. And only when it's in the proper polar form, meaning there's a plus sign between the two, then we can cis abbreviation. Here we're going to see what happens if we multiply or divide two complex numbers. We have z1 and z2 in its polar form. Here, if we multiply the two complex numbers, we'll see that their modulus will be multiplied together, and however the argument will be added together. And similarly for the division, we can see that R1 is divided by R2, meaning the argument of Z1 is divided by the argument of Z2. And for the argument, it's theta 1 minus theta 2. So that will be our new argument. So a simple way to remember this is multiply the modulus and add the argument. And you can change it up when it comes to division. The two propositions that we have just learned can be directly linked to the Moivre theorem. Here we have z to the power of n, and so for the modulus, it will be similar to the absolute value of z multiplying together by nth time, so it will be the modulus to the power of nth. And for the argument, similarly, it will be theta being added together again and again by nth time, so it will be n times theta. Here's an example to practice on the Moivre theorem. We have 2 plus 2i as our complex number, and the question asks us to find the exact value of 2 plus 2i to the power of 5. First, we have to convert this into polar form. So let's find the modulus first. We have the modulus equal to square root of 2 squared plus 2 squared, which is equal to square root of 8. And for the argument, let's draw an Argand diagram. Here we'll have the argument equal to tan minus 1 of 2 over 2, which is equal to pi over 4 radian, which is also equal to 45 degrees. And we will assemble this into our polar form, which is equal to square root of 8 times cis of pi over 4. Here, let's power this to power of 5, which is equal to square root of 8 all to the power of 5 times cis 5 times pi over 4. Now let's draw our new complex number into the Argand diagram. We will just focus purely on the argument. We have 5 pi over 4. So basically it will be around this area. And from here you can see that the imaginary part is of negative value as well as the real part. So we should keep that in mind when we plugged in to the calculator. So the question asks us to find the exact value. So it's best to show our Cartesian form. So we'll have to find the real part. Basically here you just reverse the process of converting Cartesian form into polar form, which now as we have the argument, to find the real part first, we can use this input. We'll have square root of 8 to the power of 5 times cosine of 5 pi over 4 will be equal to the real part. Because it's because cosine of the argument is equal to the opposite side, which corresponds to the real part, and over the hypotenuse, which is our modulus. So this will be our real part, and if we put that into the calculator, we'll have minus 128. And for the imaginary part, we'll just change the cosine into sine. Thus we'll have minus 128i. And here we'll have our results. Now we can try to do a past paper question. So this is a screenshot of it, and you can pause the video and try to do it yourself at home. So now let's do it together. So first we're going to find the modulus of z and w. So we are given two complex numbers above. This is the multiplication principles that we have walked through before. So we have the modulus of z times w is equal to 2 times 8, which is 16. Okay, moving on to b. Find the argument of z times w in terms of k. So we have cos theta over 5 plus I sine theta over 5 is the argument of z. And we have cos 2k pi over 5 minus I sine 2k pi over 5. So we have mentioned this before. This is not in polar form, so we cannot add this together. However, if you transformed it by putting the negative sign before theta, we can just execute the simple multiplication principle. So instead of cos 2k pi over 5 minus I sine, we're gonna have cos minus 2k pi over 5 plus I sine minus 2k pi over 5. So this is the argument of w. So we're trying to find the argument of z times w. So it will be argument of zw is equal to cos of pi times 1 minus 2k over 5 plus I sine pi 1 minus 2k over 5. From here we have the argument is equal to pi times 1 minus 2k over 5. Moving on to C, so they asked us to find the minimum value of k. So k is in the argument. Normally, I would use the range that we have discussed for the argument, which is between 180 and negative 180. However, before resorting to this method, let's try to find some clues in the question itself. So in the question, it states k has to be positive natural number. So from the second clue, let's try to draw an Argand diagram. We have I and R. Since z times r are a natural number, it has to lie on x-axis. So it's can either be here or here. So from here we can deduce that the argument theta has to be equal to 0 or pi, or at least the multiple of pi. So from here we can deduce, we can write down, since z and w a natural number, so the argument is multiple of pi. And we write down what the argument is. Pi times 1 minus 2k over 5 is the multiple of pi. So equal, let's say, n pi. And here n has to be a natural number as well. So 2 minus 2k has to be divisible by 5, since for the condition we have stated earlier. From here you can test out a few options, and like 2 minus 2k is equal to 0, or 2 minus 2k is equal to minus 5, 1 minus 2k is equal to 5. So we're trying to keep it as low as possible, since we're trying to find the minimum value of k. And so we can again test if the answers are right for each option. If 1 minus 2k equals 0, k has to be equal to 1 over 2. We cannot use, since in the question it states that k has to be natural number. So, and if we have 1 minus 2k is equal to minus 5, we can plug that in the calculator. And we have k is equal to 3. Satisfied the question. And we're going to test out the last one. If 1 minus k is equal to 5, k has to be equal to negative 2, which again we cannot use because k is positive. And so from here we can see the answer is k is equal to 3. Here we're going to learn about finding the roots of complex number. We have our complex number z to the power of n equal to c. Here we're going to take into account both cases where c is a real number and c is a complex number. So here's a visualization. We're going to have c being equal to 1. So the whole thing will be z to the power of n equal to 1. Next step is to convert both sides into its polar form. And we're going to assume the polar form of z is equal to r cis theta, with r being the modulus and theta being the argument. So applying the Moivre theorem, we're going to have r to the power of n times cis of n times theta being equal to 1. And based on the Argand diagram on the right hand side, we can see that 1 is basically equal to 1 cis of 0. So equating two sides, we're going to have the modulus equal the other side's modulus. So r to the power of n is equal to 1. So we can just deduce r is equal to 1. However, the argument is a bit trickier since here we have cis of n times theta being equal to cis of 0. However, we cannot just stop with n theta being equal to 0 since we're trying to find all the possible roots of this function. So instead of just 0, we're gonna add it by k 2 pi, with k being the constant. So here you can see that if we add 0 by 2 pi or just any value by 2 pi, it's gonna return to its original value. So basically no change is made there. We're just trying to find all the roots possible. So we're gonna times 2 pi by k. And here k will depend on the number of roots, or in fact just the power in the question. So basically k will depends on n. Here's an example. We're gonna have n being equal to 4. So we have z to the power of 4 equal to 1. First, all we have is 1. So let's convert that into its polar form. So 1 will be equal to 1 times cis of 0. And here, as we've mentioned, cis theta is equal to cis theta plus k times 2 pi. So it'd be 1 times cis 0 plus k 2 pi. Now our objective is finding z. So we're gonna have 1 cis of 0 plus k 2 pi here. And applying the Moivre theorem, we're gonna have 1 times cis 0 plus k 2 pi over 4. So this will be our z value. Now the next step is to find all the roots of this function. So let's go back to our question. Here we have the power of z is 4. And so we can deduce that there will be 4 roots, meaning there will be 4 values of k. And some things to note is that some students mistake by starting with k being equal to 1. However, we will have to always start k as 0. So again, there will be 4 values of k, starting first with k equals 0. And so we have z being equal to cis to 1 cis 0. So basically 1. Next is 1, k being equal to 1. And so we have value of z being equal to 1 times cis of 2 pi over 4. So 1 cis of pi over 2. Next, gonna continue with the remaining 2 values of k here. Here we already have 4 values of our roots. And you can stop at this step. However, I saw that most question banks would require you to put this in their exact form, meaning the Cartesian form. So of course you can always convert it. So the first value we already have 1. The second one you can put it in the calculator, or this is pretty simple. Since if we have the argument being equal to pi over 2, so it will basically equal to I. And here the next one we have the argument being equal to pi, so it will be equal to minus 1. Similarly, the final one is minus pi. Next, we're going to learn about the case where c is a complex number. Here we have an example z to the power of 3 is equal to minus 2 plus 2i. So first we have to convert the complex number into its polar form. First, the modulus will be equal to 2 squared plus 2 squared, which is equal to the square root of 8. You can keep it like as it is right now. And for the argument, you can again draw the Argand diagram. Here we have our complex number, and some will mistake by calculating this angle. However, the modulus that we are looking for is this angle instead. So you can always calculate the alpha first, which is equal to tan minus 1 of 2 over 2, which is equal to pi over 4. And to calculate the argument, which we'll call theta, we'll have theta being equal to pi minus pi over 4, which is equal to 3 pi over 4. And so we have z to the power of 3 is equal to square root of 8 times cis of 3 pi over 4. Square root of 8 times cis of 3 pi over 4 plus k2 pi. And to find z, we'll have, and so since we have the power of 3, so there will be 3 values of k, starting with k being equal to 0. So z will be equal to, and we continue with the 2 remaining values of k, which we'll have. So here are the 3 roots of the complex number. You can always convert them into Cartesian form when they ask you for the exact value. So we have, so applying the formula that I've mentioned before, for the real part, it will be equal to the modulus times the cosine of the argument. So plugging into the calculator, we'll have 1 plus, and for the imaginary part, it will be the modulus times sine of the argument. And continue the same for the remaining values. We'll have so here are our value in Cartesian form. I'll write the input you will put into your calculator to find the corresponding real values and imaginary values from polar form. So to find the real part, you're going to use the modulus times by cosine of the argument. And for the imaginary part, similarly, you just need to change cosine into sine. Here's another past paper question on complex number. You can pause the video and try it yourself at home. Now we're gonna do it together. A asks us to find the roots of the equation w to the power of 3 equal to 8i. So this is the finding the roots of complex number part. So now to tackle this, we have to convert 8i into its polar form. You should always draw an Argand diagram first to just visualize where the complex number lies. So here 8i's will be here. And so we'll have the modulus equal to square root of 8 squared plus 0 squared, because we have no real part, times cis of, normally you can plug it in the calculator, but here you can easily see that the argument is pi over 2, so we have pi over 2. So thus we'll have 8 times cis pi over 2, which is also equal to 8 times cis pi over 2 plus k2 pi. So this is an important part. And now to find w, we'll have the third root of 8 times cis of pi over 2 plus k2 pi, everything over 3. Now you're gonna calculate this. We have 2 times cis of pi plus k4 pi over 6. Now we're gonna examine the power that is in the question. So we have the power of 3, thus having 3 values of k, or 3 values of the roots. We're gonna start with k equal to 0. And thus w will be equal to 2 times cis of pi over 6. And similarly, you're going to calculate for the 2 remaining values. Now we're going to convert these 3 values into their Cartesian form, as we are having it in polar form right now. So as for the formula that I have mentioned, we're going to calculate the real part and imaginary part based on trigonometry property. So now that's our part A. Moving on to part B, here the question asks us to identify the roots that satisfy the condition where the real part of the complex number is equal to 0. Given this form, we have to express z in the form of a plus bi. So first we're gonna find the roots that satisfy the condition. So here, judging from all the 3 that we have found, we can see that the final one meets the condition. So we have w1 is equal to minus 2i. And next, we're gonna write this in the given form from the question. So it's gonna be minus 2i being equal to z over z minus I, which you can also put in a plus bi as z. So we're going to have a plus bi over a plus bi minus I. Here you're going to do cross multiplication and then solving it like a normal function. So we're going to have, as we have already discussed from the beginning, we have I squared being equal to minus 1. So we're going to have minus 2ai plus 2b minus 2, which is equal to a plus bi. Here we're going to equate the real part and the imaginary part from 2 sides. Here, this is our real part, as there's no I, and this will be our imaginary part on the left-hand side, which correspond to the imaginary part on the right-hand side. And so by equating these two, we're going to have 2b minus 2 equal to a. And for the imaginary part, we're going to have 2a equal to b. We're not going to use I in this. And from here, you can plug it in the calculator on solving multiple functions, or you can use simple displacement method. Having calculated the values, we have a equal to 2 minus 2 over 5, and we have b equal to 4 over 5. And then we're not going to stop here, as the question asks us to express z in the form of a plus bi. So we're going to express z as minus 2 over 5 plus 4 over 5i. So here's our answer. Now that's the end of the video. I hope you find this helpful, and you can always refer back to each section to reinforce your knowledge on each aspects of complex number.